Okay, Kareem, I'm done.
Okay. So can you please go ahead and join the presentation? I think you've already done.
Yeah, I have.
Okay, great, perfect. Then let's start. So again, good morning, everybody. This should be episode 2 of part 1. Just to remind you, part 1 was talking about what's happening there. By there, I mean what's happening in the Hematology Oncology office. For the first episode, we've been talking about the hematologist oncologist himself, and now we are talking about the hematology and the oncology. So today's presentation is going to be divided into two main parts. First part is talking about oncology and cancer, and the second part is talking about hematology. Okay. Please, when we are talking, if you have any comment, any idea, any question, go ahead, unmute yourself and start talking. When I revised the video for the last time, nobody has interrupted me. And I really wanted this be more like a conversation. I don't know how to do this yet, but I'll be trying. And I want you guys be, more helpful and more interactive. So let's start. The first thing I want to talk about is what's cancer. So cancer is a disease, a malignant one, a very bad one. It's caused by a group of changes. It's like a gang of genes that's working, and try, in harmony together, just trying to make your life worse. So they are like a gang of a gang of genes that leads to an abnormal cell behavior. For the first, the body response starts to be very aggressive because of this change in the behavior of the cells. But then after that, those cells really got the control, and if they are angry, they can destroy everything. So it's a group of genes that leads to abnormal behavior, which finally leads to form a mass of invading cells. So they actually invade on the other cells in the next and surrounding structures, and then they go metastasis in the other parts of the body. So this is basically the definition of cancer by the WHO. It's a disease caused by a group of gene changes that leads to abnormal behavior of the cells and the invasion of the next or the surrounding tissues. Cancer was responsible for 15% of all human deaths in the last year. So cancer only, by itself, is just responsible for 15% of human deaths. And then let's talk about how cancer happens. So cancer basically is a problem of tissue growth. Usually what's happening in our body is, we are born and we are, growing until we die. So the problem, the process of tear and wear that's happening in the human tissue is an ever continuing process. But then if there's something wrong happens with the growth, and this yields a problem of growth, this is most probably going to lead to cancer caused by multiple genes. So this is a very important concept, that it's not like other diseases. Cancer is not like any other diseases. Cancer, you have to think about cancer more like a failure. So it's caused by a lot of causes that's interacting together to disrupt the system, and any disruption of the system of growth is going to be cancer. So it's not like it's not like common cold, that there is a virus that causes pathophysiology in the tissues that results in the common cold disease. No, cancer is more complicated than that. Multiple genes, multiple factors, anything that can disrupt the system can lead to cancer. So, and why this is important? Because of the way we're gonna treat cancer, because it doesn't have, a treatment that's this drug work on this receptor and this leads to cure of cancer. No, because it's more like failure of the system. Many causes can cause failure of the system, and here comes the importance of diagnosis. And we want to, a diagnostic lab like ours, its complete mission is to find why this cancer is happening, which part of the system is weak, which part of the system has failed and led to this cancer. So I want you always think of this as a multifactorial process. And it's very important that we develop and we keep developing our tools and our tests to know more about the causes of the cancer. And this is, it's gonna come later to know, like the next generation sequencing. Why is it so important? Why flow is so important? Why adding more panels is so important? Why adding more tests is so important? Because even with the tests that we know right now, even with all the development we've done with cancer, we even, I'm talking about even leukemia itself, we are still knowing more and more and more about leukemia and about the causes of leukemia, and we are still developing more tests to know more about the causes of leukemia, and this helps us with the right, the choice of the right treatment. So anybody has any idea about this? Any thoughts? This is a really important concept. Okay, so this multifactorial process. Oh, is anybody gonna talk? Okay, so this multifactorial process leads to the transformation of cells. And I have been trying to find an analogy for this transformation, and I think the Hulk transformation is really interesting transformation analogy, because it exactly happens like this. The normal, benign, cute cell, it just starts to change, become more angry, more aggressive, more invading to the next tissues, and it's caused, by factors that's out of control of the cell. So it's and it yields this, angry, destroying, malfunctioning cell. So think about the cancer genetics, the cancer, pathophysiology as a transformation. It happens due to, it's a multifactorial, and it happens on multiple stages, multiple steps. So staging a cancer is really important. And this is the second important point about the diagnosis. So the diagnosis says that there is cancer, and then it says why this cancer is happening, and then it says in which stage we are, because the treatment is going to be very, very different from, between different stages. So as we grow, as we become more malignant, we need more aggressive treatment, more aggressive types and lines of treatment. Sometimes even surgery can't cure the problem. You know what I mean? So this transformation that happens in multiple stages is very important concept to understand, because this is a very major rule that the diagnosis and the diagnostic lab like ours is working on. So a doctor wanna exactly know why this cancer is happening, and he also wants to know on which stage we are. And after everything is done, this leads to undesirable survival of the fittest. So because the cancer transformed cell is really big, really strong, and really crazy, it can survive. And for it to survive, it takes the nutrients and the space from other benign cells. And it finally leads to the undesirable survival of the fittest. So this is basically how cancer happens. And to dig more into the scientific details, I just want to remind you guys. So this is the cell. It should be a human cell, but this is not a human cell, of course, because it has a flagellum. But that's fine. Let's say this is a human cell, and each human cell, it has a nucleus. And when we zoom into the nucleus is the genetic material. So when we zoom into the nucleus, we find it formed of 23 pairs of chromosomes. They are complicated and intermingled together, but basically if we can separate them, we're going to find them 46 chromosomes, 23 pairs of chromosomes. And this is that the process of karyotyping to get this complex dense material to be arranged in 23 pairs of chromosomes. And in each chromosome, this is a super coiled thread string of double-stranded DNA. So basically it can go up like 60 miles of length in each chromosome. The DNA thread, it's super coiled. But if you can uncoil everything, it becomes the double-stranded thread of DNA. So I want you to understand the difference between both terms. This is a chromosome. Each cell has a nucleus that has 46 chromosomes. Each chromosome is formed of a very long thread of DNA. Each thread of DNA is double-stranded, and it's formed of the nucleotide bases. This is like the some chemical stuff, but the genetic information is stored in the arrangement of those bases. So we have 4 kinds of nucleotide bases. The genetic code, the genetic information, is coded into those is using these 4 nucleotide bases. The arrangement of them, the sequence of them, is coding for the information. So each let's say like 60 bases, 60 bases in a sequence. This is called a gene. This sequence can produce a protein. This protein has a function, so we call this gene. So each number, it has nothing standard. Maybe a gene can be 60 nucleotide bases. Another gene can be like 3 million nucleotide bases. There's no standard for this. But so the chromosome is formed of multiple genes that's coded on the DNA strand. Is this clear? Can you understand the difference between a gene and a chromosome? Because this is really important. Please go ahead and acknowledge that you understand this.
Hey, Kareem, it's Jean. I got it.
Okay, great. So Vanessa.
Yes, I understand it.
Okay, Omar.
Yeah.
Lori. Okay, great. So let's move on. So cancer is basically DNA fault. It can happen in different scales. It's either a chromosomal abnormality. So this is the chromosome. A chromosomal abnormality means like we lost part of the chromosome, or we have a duplicate chromosome, or we lost a complete chromosome. And this is gonna change the DNA material, and when it changes, this is gonna lead the transformation of cell and finally produce cancer. But it can happen on this big scale. We lost a very big part, a very big group of genes, because we lose a complete part of the chromosome. Or it can happen in a very small scale, like even 1 nucleotide base change. They call it point mutation. And this is gonna change the sequence, and when it changes the sequence, this is gonna change the protein that's formed, and this is gonna function in another way, and this can lead to cancer. This gene is involved in the process of the cell division and growth. It's gonna lead to cancer. So I want you to understand that the problem of cancer is happening due to a DNA fault. And this can maybe happening on a chromosomal scale or on a gene scale. And the chromosomal abnormality may be, loss of chromosome or duplication of a chromosome, or it can happen, on a large scale gene mutation, maybe translocation, like loss of a part of chromosome that that detaches from its chromosome, its original chromosome, and go be attached to another one. And this is the Philadelphia chromosome. Philadelphia chromosome is a very, very common and important thing in the field of leukemia and the field of hematology. And of course, I think all of you guys know the BCR-ABL gene and the BCR-ABL test. The BCR-ABL test is very, very important. It's very, very commonly requested in our practice. And this is basically the BCR-ABL is an example of the large-scale gene mutation, where part of the gene number of the chromosome number 9 detaches and go be attached to the chromosome 22, and this leads to leukemia, the CLL leukemia, chronic lymphocytic leukemia. So when a doctor wants to know that if the patient, when the doctor basically requests a BCR-ABL test, he wants to know if this leukemia is caused by this common, large-scale gene mutation. And this is, of course, is gonna, tell him what's happening with the patient, why this problem happened, and what should be the best treatment for him. And we're gonna go through the BCR-ABL gene, when we are talking about leukemia. So don't worry about it right now, but just, I want you to know that this is an applied knowledge, that this is very important for a doctor to understand. So a chromosomal abnormality, this is, the BCR-ABL. So this part of the chromosome number 9 goes to the chromosome number 22, and vice versa. It's called a translocation. This leads to the Philadelphia chromosome. So basically, all our body functions are mediated by proteins, and all our proteins is coded in our DNA. So a bad DNA is going to lead to a bad protein, and if this protein is involved in the cell division and cell growth, it's going to lead to a crazy cell. Crazy cell, of course, is a malignant cell. So now I want you guys know that there are two types of genes that are really important. So we have, the Genome Project has been working to understand, to uncover all those genes that we have in our DNA. And we have really lots of genes, like tens of thousands of genes. But, two groups of those genes are really important in the cancer forming process. I think we lost somebody on the presentation. Who is it? Who's not on the presentation?
I'm on point.
Okay. Lori, are you on the presentation?
Yes, I'm on.
Omar?
Yeah.
Vanessa?
Yes.
Okay, so how come we have only 3? Okay, no problem. So the idea, so I was talking about we have like tens of thousands of genes in our DNA. But only 2 groups of genes are really involved in the process of cell division and tissue growth. And they, when some, a mutation happens with those 2 groups of genes, this is most probably going to yield a cancer. So those gene mutations either happens in a group called oncogenes or tumor suppressor genes. So, if happens and there is abnormal activation of oncogenes, this is going to lead to cancer. Or abnormal deactivation of tumor suppressor genes, this is going to lead to cancer. So to understand exactly what those genes do, we want to understand what's happening in the cell cycle. So for each division in the cells, we grow by cell division. For each division of a cell, there's something called the cell cycle. And to understand the cell cycle, we have to think about this, very basic thing. So the cell is one cell. It goes, to increase the DNA material that they have, and then the mitosis phase, and then they grow. Each one, they divide, and then they grow to a bigger cell, and then they divide, and then it goes on and on and on. So the tumor suppressor genes are the genes that keep the cell in the resting phase, which means those genes produce proteins. Those proteins prevent the cell from dividing. And in order for this cell to go ahead and divide, those tumor suppressor genes have to be deactivated. And for them to be deactivated, normally what's happening in my and yours body is they get signals that deactivate them, and then the cell starts the dividing process. If there's anything wrong with those genes, that they are permanently deactivated, or they respond in a wrong way to the signals, so they are not working, so this cell is going to be going on and on and on and on and on, and this is going to lead to cancer. Indefinite number of divisions, which means a tumor. The second group of genes are the oncogenes, and those oncogenes are the genes that get this cell to grow and start having, storing those nutrients important for, the synthesis of the DNA, and, preparing the cytoplasm for division and all those kind of stuff. So those genes have to be on for the cell to be working. And they usually, what happens in my body and your body, that they respond to signals that activates them, so they would start producing proteins that prepare the cell for division. So if those genes are always on, or are responding to signals in a wrong way that makes them activated in a wrong time, this is going to lead to an indefinitely dividing cell, and this is basically cancer. So to understand the idea, any gene mutation that lead to activation of oncogenes, the green light, or deactivation of the tumor suppressor genes, the stop sign, is going to lead to cancer. This is, basically the idea what's happening in the cancer. I want you guys started grasping the idea. Lo, go ahead and say anything.
I got it.
Okay. Do you have any questions or any comments, or do you think anything is not clear? Do you understand why this is important?
Yeah.
Because basically this is what our lab does. It wants to understand what's happening in the background. Jean, can you please unmute yourself, please, if you're not talking? Because we have an echo. Okay. So this is basically what's our lab doing. It tries to uncover those kind of high ticky stuff, to understand what's happening to those genes, what's happening, what kind of mutation has happened, why are they completely on or completely off, what's happening with them, what's wrong with them. So now there's a theory that says it's called the 6 hallmarks of cancer. And this is, this was a very famous scientific paper that was completely revolutionary in understanding cancer. It said there is 6 mechanisms that that change happens and yields cancer. And to understand them basically with no Chinese language, I'd say they are the 3 phases, 3 things: steady, ready, and go. So they prepare the cell to be completely malignant. So to be steady, to start prepare for being cancerous, for being malignant, the cell has to escape death and be immortal. What does this mean? So basically, each of our cells has a button that when you click on it, the cell started a programmed cell death. You know, each cell has a specific lifetime that after, when this lifetime expires, it just go ahead and kill itself. Killing itself, it's called apoptosis, which is a Greek fancy word for, suicide. So any change in the oncogenes or tumor suppressor genes is going to lead to no apoptosis. No apoptosis means the cell escapes death and starts a cycle of limitless divisions. Basically, the cell has an immortal potential because they can't be killed by themselves. Usually my cells kill themselves, but those cells have the potential of limitless divisions. So to be steady, to be prepared to be cancerous, the first thing they have to do is to escape death and be immortal. And then they have to be always firing, never stop dividing. They usually don't respond to anti-growth signals. Usually in my body there's continuous firing of anti-growth signals that keeps the cells are really regulated by growth signals and anti-growth signals all the time, and there is a fine balance between them that leads to the right perfect thing happening in my body. But in those cells, they have a very high self-esteem. They don't need growth signals from outside. They are producing their own self growth signals, and they do not respond to anti-growth signals, so they never stop. And then when they are ready to do cancerous stuff, and what's cancerous stuff? It's to invade. So they start getting supplies because they are really growing very huge and very progressively. So they start building their own blood vessels to maintain the nutrients sufficient and necessary to do this rapid growing stuff. So usually in my body and in your body, there is a current of blood that's going through the tissues and grabbing enough amounts of nutrients to all the cells. But those cells are really preparing for a war, so they produce their own blood vessels, and this is called angiogenesis. Angium in Latin means vessel. Genesis means production. So they produce their own blood vessels to start getting more and more nutrients to prepare for the invasion of the next tissues. And this is basically the 6 hallmarks of cancer. And to understand this, I'm gonna go ahead and show you this in the fancy scientific words. So in a fancy scientific word, the 6 hallmarks are evading programmed cell death, no apoptosis, and then the limitless replication potential. This means they are completely immortal, and then developing blood vessels, the angiogenesis, or having the nutrients, and then the tissue invasion and the metastasis, to the next tissues. They have self-sufficiency in growth signals, and they have insensitivity to anti-growth signals. Those are called the 6 hallmarks of cancer. Do you started grasping the idea, understanding what's happening with cancer, what's wrong with this guy? Hello? Don't you want to say anything?
I think you're doing a great job.
Okay, thank you. I just want you guys get the time and comprehend what's wrong with cancer. What's happening with the cell? What's wrong with it that finally produces cancer in this aggressive, ugly way that we see? Okay. Great. So now let's go ahead and discuss what are in our arsenal to defeat cancer. basically to the modalities of cancer treatment has been three basic stuff, surgery, chemotherapy, and radiotherapy. And then we started having, more and more, recent treatments. So the old and the most, ordinary thing to cure cancers, of course, I'm talking about solid tumors, not leukemia or lymphoma, but let's say lung cancer, breast cancer, anything that a medical oncologist is going to work with other than blood tumors is going to be mostly treated by surgery, which basically means if there is something wrong with this part of the tissue, let's say there is this small nodule in the breast, there is something wrong in this breast tissue, okay, let's go ahead and remove it. But first, we have to make sure that there is no distant metastasis. And distant metastasis means like there is no small parts of this tumor that has break apart from the main tumor and go through the lymph system and the blood system to other parts of the body and started, a second focus for the tumor. As long as this hasn't happened, most of the tumors can be cured by surgery, basically by removing the tumor with a safe margin, with a safe margin of healthy tissue around this tumor. And this most commonly going to be enough to remove the tumor and start the next treatment modality. The second most important treatment modality is chemotherapy. And of course, you guys have been through a lot of hematology oncology offices, and you know that there are chemotherapy patients there that needs, the chemotherapy infusion. And this is a huge industry. With pharma industry, they are all the time developing new drugs, trying to make them more specific, trying to make them more effective. And basically what chemotherapy does is, this is drugs that interfere with the normal division of cells, so they would prevent all the cells in the body from, dividing. And by this way, they are killing the tumor, because the tumor has to be highly dividing cells. And if no cell in the body is dividing, so the tumor is going to die. That's why, basically why, with chemotherapy, some patients start to lose their hair, because usually the tear and wear in hair is really fast. So we lose a lot of cells, and they have to be dividing all the time. And because, all the cells in the body are prevented from being dividing, so they start, losing their hair and having all those side effects of chemotherapy. So basically, chemotherapy says enough is enough for all the cells in the body. It goes, for the malignant cells and for the benign cells as well. And then there's radiotherapy. And radiotherapy basically is, we are trying to, nuclear bomb the malignant cells. Because the malignant cells are on the moving state, they are highly dividing, so they don't actually have the time to make sure that everything is going okay. So with me and you, when our cells are dividing, before a cell divides, it has to recheck its DNA. Make sure that the DNA is good, is working, it has no changes, and everything is going very well with it. But those tumor cells, because they are really highly and fastly dividing, they don't have enough time to recheck themselves and make sure that they are going okay, and make sure that they are doing the right thing the right time. They are not able to recheck their, the DNA material and make sure that the next cell is going to look exactly like the father cell. So they don't have to do that. They don't have the time to do this. And what radiation does is it changes the DNA material in a way that prevents it from being replicable, from being able to be replicated. You know what I mean? Does it make any sense for you? Any DNA for a cell division has to be replicated for an exactly similar set of chromosomes. And if the DNA is not in the perfect shape, it's not going to be able to replicate itself. And this where radiation works. Like it breaks the DNA parts, it breaks the DNA, it changes its way, it changes the way it's coiled or helix. It changes it all the time. For a normal body cell, before it goes to the next division, it's gonna have the time to figure it out and fix the DNA problem that's happening. But for a tumor cell, it doesn't have the time to do this, so it's most likely gonna die. And that's why the patients who get radiotherapy, they get it in in pulses. Like you get a dose today, we wait for 3 weeks, get another dose, wait for 3 weeks, get another dose. And why this? Because we want to give a time for the normal cells to start fixing themselves. And by this mechanism, we are kind of targeting only the tumor cells, because we know that they don't have the time to to check the DNA and replicate the DNA in a normal ways. So most probably they're gonna die in their replication phase. The DNA is gonna be break apart. It's not gonna be able to live and replicate anymore. So this is basically the general idea of how radiotherapy works, and we developed it because chemotherapy is really general and it can kill all the cells, and so we can't stop it. Like when a patient starts having infusion with chemotherapy, it's gonna affect all the cells, and he has to take chemotherapy for a long period enough to kill the tumor cells. Otherwise, if we stop the chemotherapy, the tumor cells is gonna start replicating again. So that's why we started having radiotherapy, and this is kind of targeting the tumor cells more than the normal cells. And there are two ways of administering this radiotherapy. It's either external beam, which means we actually radiate the person from outside with a radiation beam directly going to the place where the tumor is. In blood tumors, we radiate the bone marrow. In breast tumor, we radiate the breast. In lung tumor, we radiate the lung. So we direct an external beam directly to the tumor. Or it can be a brachytherapy. Brachytherapy means the patient gets a capsule of radioactive material, and he administers it with juice, and then it starts radiating from inside the body. It's very difficult. It's very sensitive kind of science, that there is only a doctor specialized in the way of administration of the radiotherapy. A radiation oncologist. He is a guy that spends his entire life trying to study which dose and which radioactive material and which way of administration for which cancer, because it's really kind of borderline. A wrong dose of this treatment can kill you instead of giving you a perfect treatment for your cancer. So this is the idea, and you can understand how dangerous surgery or chemotherapy or radiotherapy, because we at the end of the day, we want the patient have a good life. Think about it. If a patient has a cancer in his bone, we're gonna cut his limb, or do mastectomy, or do lobectomy in the lung, or do whatever. And this is in medicine there are two terms: mortality and morbidity. Mortality means the potential of death. Morbidity is the potential of bad life. So we want to always control the morbidity. We can control the mortality. Like this treatment, either surgery, drugs, or radiotherapy, is gonna enable the person to live long, but it's gonna increase the morbidity, which means he's gonna live long, but he's gonna lead a bad life. So this is why the doctors started seeking more and more modalities of cancer treatment, because those cancer modalities treatment are not good. They're not gonna, the person, I'm gonna increase his life expectancy, but he's gonna lead a bad life. That's why we started having those recent modalities. The most recent and the most I love it personally, it's the targeted therapy. And the targeted therapy, they have been developing drugs that can find what is the change that happened in the malignant cell. Do you remember, guys, that for a cell to be malignant, there has to be a change in their genes? So this change marks this cell. Let's say if this change makes the cell red, so any cell that's red is going to be malignant. Any cell that's not red is going to be good. So if we can find a drug that only target the red cells, so we are actually targeting only the tumor cells, killing them, and giving the chance for other cells to be perfectly fine and dividing, so we can cure the problem with chemotherapy. And this is the whole idea of targeted therapy. And because cancer is mostly the change is happening due to a gene mutation, so if we can find a drug that works only with the gene mutated cells, that can find the gene mutation that happened in the cell, so this drug is going to target only those kind of cells. And this is where the next generation sequencing is working. So, and this is really exciting part of the diagnostic process. They are trying to find each and single gene change that's happening in the cell. So let's say a doctor has a patient, and the patient has leukemia, and he wants to know which gene exactly has changed that led to the failure that finally led to leukemia. And in order to understand this gene, he has to do a molecular test. So he suspects, like, let's say 8 genes, 9 genes, 6 genes, 70 genes, we don't know. He may suspect a full spectrum of genes. So he sends the specimen to the lab and says, okay guys, can you please find which genes of those are mutated? Because for each gene he can find a drug that specifically works with the mutated gene, this mutated gene. And this is what we are working on. So we have a test for each gene. Now in PsyParadigm we have almost like 20 next generation sequencing. Let's say NGS. We have 20 NGS tests which test for 20 genes. But think about it. New genomics, they develop 70 new tests per year in the next generation sequencing. There is huge potential out there. They validate 70 to 80 new tests in the field of next generation sequencing per year, and we still have 20. And now we are, we have hired an expert who has his expertise only in validating the next generation sequencing tests. We are trying to develop this portfolio, this menu, and increase them and increase them. And this is going to enable us to work with the medical oncology doctors. So, to understand the idea, any medical oncologist out there, he's working with cancer. And he's working with all types of cancers, with breast cancer, with lung cancer, with all types of cancers. So why are we only working with the hematology oncology? Is any of you guys has this idea? I'm sorry, we are a little behind our time, but this is really important. Please go ahead and say why aren't we getting lung specimens or breast specimens or anything? Go ahead and share what you think. I'm sorry, your voice is really low.
My assumption is that we can't do all the tests that they're looking for.
Yeah, we can do some of them. So why aren't we going to them? Why aren't we selling some of those tests? Like, we can do some tissue stains. Why aren't we getting any volume in this? And why aren't we, as a sales force people, why aren't we going after them? Why are we going only after the hematology oncology part of their work, which is, by the way, which is like 3% of their cake? The cancer, the hematology cancer is only 3 to 5% of the cancer cases the medical oncologists see, and the other pathology labs are working on. What do you think? What do you think, Vanessa? What do you think, Lori? What do you think, Omar?
Why don't you just fill us in, man?
I'm sorry.
Why don't you just fill us in with the correct answer?
Okay. I mean, I just want you. I mean, this for me when I was first working as only as a salesperson. Before I started, doing this kind of research, I didn't understand this. Why aren't we going after the breast cancers? You know, guys, that we do the BRCA test, right? The BRCA test is for breast cancer. We do it. Why aren't we going after them? Because basically, to do this kind of stuff, we have to have a specimen. And think about it. To get a breast specimen, how can we get a breast specimen? It can't be done without surgery. It has to be done, by surgery. And for this to happen, the patient has to be admitted to a hospital, because this is a complicated procedure. It's an operation, so he has to be admitted to the hospital. And if he's admitted to the hospital, most probably, and the law forces the breast specimen to go to the pathology lab of the hospital first, and then they can do some stuff on it, or they can send it out. And because we don't have this kind of, we are not contracted with so much hospitals, so we are not getting them. But we are going after the offices of hematology oncology, because we can get the specimen, the blood specimen or the bone marrow specimen. It can be done in the office. Have you started to get the idea? These specimens are easy to get from the body. The patient doesn't have to be admitted to the hospital. It's not an operation. So we are going after them because the specimen is really easy to get, and it's only the hematologist, oncologist say to where to send this specimen. So basically, so why aren't we going after hospitals? Because for hospitals to have a contract with them, you have to provide them with a full menu of tests that you can do a lot of tests, because the hematologist oncologist can order like 70 tests per specimen. And if you don't do them all, he's not going to send half of the specimen to you to do 20 tests, and send half of the specimen to New Genomics to do the other 50 tests, while New Genomics can do the entire 70 tests. So our current challenge is to develop as many as we can of the next generation sequencing tests, so those doctors we can provide all the tests those doctors commonly use, so we can provide something in our menu to the hospitals so that we can get their contracts. Have you started to understand the idea? Have you started to understand why next generation sequencing is really important?
Of course, yes.
And why have we been talking about next generation sequencing for a long time? We need the next generation sequencing. It's gonna open a lot of opportunities for us, because it's gonna make us more appealing to hospitals. And it's a lot of tests. And just I want to give you this piece of information. I know a lab that's called Guardian 360. It's based in California. They have raised $180 million in the past 2 years just to develop next generation sequencing tests. And guess what? They have developed this technology to get liquid biopsy, so they can get the breast biopsy or lung biopsy or anything from the patient without admission to the hospital, without going to the operation room. They can just get a breast biopsy with a needle. I'm not talking about the fine needle aspiration, by the way. This is a different procedure. But I'm talking about a real tumor biopsy just with a needle, which can be done in the outpatient. They can just get anything they want about lung cancer from the blood. So you just give them a blood sample and they will find whatever is happening. So they are really smart, and this is a really promising field. Those guys have a huge amount of fun just to develop this kind of test. So they can go to the medical oncologist, like this Guardian 360 lab. They are not working with hematology stuff. They're just working with other tumors, solid tumors. They are not working with hematology stuff. But they can go to the office of a medical oncologist Just to remember, we only work with 5% of his volume of patients. You know, you remember that the hematologist oncologists see in average like 70, like spend 70 minutes for each patient, for working like 8 hours. Let's say he sees 3 patients per hour. This means like he can see 24 patients a day. And then in a practice that has 4 doctors, they have almost like 100 patients a day. And if in the most part they can send you like 3 specimens a week if they are very loyal to you. From 500 patients they see a week, they can send you only 3 specimens if they are really loyal to us and they are only sending their hematology stuff to us. So can you understand how big potential there is outside the hematology part? How big stuff can we do? Can we work with them? This Guardian 360 lab, they promised their doctors to do the stuff for the other 497 patients they see each week, just from a blood sample. They don't have to do any kind of surgery anymore. Can you understand how promising this is? How challenging this is? Are you really excited? Because I'm really excited to understand this idea. This next generation sequencing is gonna change the face of industry. It's gonna change the normal ways we are working with, and the fun thing about it is all the labs are still working on it. All the labs, all the sales reps around the country, they are still trying to understand what's next generation sequencing. Most of doctors have no idea how next generation sequencing works. I have only one doctor on all my accounts that has only sent us one next generation sequencing sample. He wanted to know if this kind of targeted therapy, one of the drugs, it's Rifamab, he wanted to know that if this drug is working with his patient or not. So this is the whole idea of the next generation sequencing. It's all based on the targeted therapy part of the treatment modalities, and this is really important. Okay, just I don't want to take more of your time. I'm gonna go very quick. So another modality is the immunotherapy. Is we transfer antibodies from other person. Those antibodies can attack the malignant cells in the patient body. So we transfer those antibodies from the normal person to the patient so that they can attack his tumor cells. And it's funny phenomena in the medicine. It's called graft versus host, because usually when somebody has a graft from other person, like let's say a liver graft, like he gets part of his twin or his brother liver tissue get transplanted to him, or a heart transplantation or something. His immunity starts to attack the graft. So it's called host versus the graft, because the graft is a foreign tissue. But this is the opposite. So we get the graft to attack the host, because we wanted them to attack them, the malignant cells in the host. So it's kind of funny thing. And then finally, there's the hormonal therapy. Some tumors, they are affected by hormones, and they are, some like breast cancer, it's affected by estrogen. If the estrogen levels are really high, they can, they aggravate the tumor. Or if the progesterone or the testosterone is high, they can, lead to tumor regression. So we can use some hormones to treat cancer. This is basically the cancer treatment modalities. I'm not gonna go to the hematology part right now. Maybe we're gonna wait for the next episode to go through this cancer part again and continue the hematology part. I hope you guys got some interesting information. Please go ahead if you have any questions, any comments, and any feedback. Go ahead and say it. After I finish, we're gonna take the test again. So please open the link of the test right now. so that you can get the test again. Hopefully you would know that the difference in your answers between the first and between the pre-test and the post-test. And I'm gonna be sending the handout right away after we finish the webinar. If you have anything to share, please go ahead and mute yourself and start talking. Vanessa, you have anything to share?
No, thank you.
Okay, Omar?
Yeah, what does it mean if I get a lower score on the test after listening to your presentation?
No problem. If you have any kind of question, you can always ask me anytime. And I'm gonna go through this. I know this information has been, really a lot today. I'm gonna go through them the next time, before we go to the hematology part. So don't worry. Okay, Lori.
Oh, I'm good.
Okay, I'm glad you got. Jean.
Yep.
Okay, do you have anything to share?
I just thought it was great. I like the way you explain things, and I think the whole analogy was really good.
Okay, thank you very much. Okay, guys, please get the link of the test ready from the Showcase app. I'm gonna be sending the handout. It has all the information. You can go through it. You can read it. Just try to deepen the knowledge that you have. It has a little bit more details than the stuff I have been saying during the webinar. We're gonna go through them again. Please read the handout before we get to the next week episode. So if you have any kind of questions or comments or things to share, you'd be able to do this the next week. Okay, thank you guys. I'm sorry we are 20 minutes late, but we have started 20 minutes late as well. So I'm really sorry for that. For the next week, please be ready like 15 minutes before the webinar. I'm gonna be sending. I know that I'm late to send the link, but I'm really I have a lot of stuff to do before I start the webinar. So please be ready 15 minutes before the webinar. I'm gonna be sharing the test and all those stuff before exactly we start the webinar. Thank you guys. See you next week.